Okay, so essentially what happens when you're trying to build these imperfect models of the real world is that you have a training corpus, and the training corpus you estimate a model. Right? So what do you mean by estimating a model? Essentially, a model is a collection of statistical parameters. They're what you call statistics. They're parameters that are properties of the data we have, the sample we have. Right? So since it's really largely reflecting the training corpus, it's not perfect. It may be an imperfect model of the real world. Okay? So we want to know how good it is. So usually there is some way in which we're going to use it. We're going to use this model in some way, some sort of inference procedure. We're going to use the model to infer some properties. And we want to know how good this is. How good is this inference going to be? Right? So depending on the setting, you have a test corpus. And you do inference with respect to the test corpus, and you see how good it is. Right? And so you get some measure that tells you how good it is. So, it depends on what you're trying to do, right? So if you're trying to do labeling, of data, is this buggy or not buggy? If you're trying to do information retrieval, there are these sort of precision recall type measures you can use. In our setting, we're really trying to assign probabilities to sentences, right? Probabilities to fragments of programs, fragments of English, fragments of German. We're trying to assign these probabilities. We want to see how good those probability assignments are. Is this a good probability assignment? So in other words, if a sentence, supposing it's an English sentence like, today the European Central Bank announced an increase in interest rates. That's a good sentence. If somebody says, today the European Central Fish announced an increase in interest rates, it's not a good sentence. Right? So a good model should understand to assign high probabilities to real sentences and low probabilities to fake sentences. Right? So when you're thinking about language models, this measure in some sense should reflect how good that probability assignment is. Right? So that's what we're going to talk about. The measure we use is called cross-entropy. Right? So we're trying to build these models that assign probabilities to a language event, a sentence, a fragment of a sentence, a fragment of a program. So first we train the language model on a data set. Right? So we have lots and lots of data. We have 500 million lines of code. We can find it like that, no problem. Right? So use this large corpus to train a model. Okay? And then we have a separate set of test events, T, that we haven't seen before, right? New programs we haven't seen before. And so for each event in this test corpus, we have a probability. And we want to know if it's a good assignment, if it's a good assignment. Okay, so essentially what this is doing is finding a way to evaluate this probability assignment. So for each program in the test corpus, right, we assign a probability. And then what we do is, we're saying, how likely is this test corpus? Right? So, so we have, let's say, 100 sentences in English as our test corpus. Right? We want to know, is this 100 sentences that we see here real English? Okay, so what we do is we calculate the probability for each sentence, right? And then we compute the product. Why do we compute the product? Because essentially there's an implicit assumption that each sentence is an independent event, right? So if you have a set of independent events and you have probabilities for each of those events, the joint probability is just the product, right? So you take the product of all these probabilities, right? That gives you the probability of the test corpus. Now, if that test corpus really is English, and your model is a good model, then it should say, yeah, this looks like English. I give it a high probability. Okay. If your test corpus is unreal English, if it's some other language, or it's bad English, then you should give it a low probability. Right? So that's this product, this pi that we're calculating is the probability of the test corpus. Now, products are hard, right? And with probabilities, you get very low probabilities, so there's a risk of underflow. So typically, this is just done using log scales. Right? So once you calculate the logs, addition is easy. Right? So, and you're not going to run into underflow problems. So usually, this is done by summing up the negative log probability. Okay. So what you end up with in the end is that if you average over the number of sentences in the test corpus, right, you end up with an average log probability per sentence, right? Per event, language event in the corpus. Per sentence, what's the average log probability? So in some sense, you can think of this as a measure of the amount of information in each sentence. Okay. So this is called cross-entropy. So remember, the way this works is, we have a model. Okay, we're going to take that model and ask the model, what do you think is the probability of these sentences? Right? You take the negative log probability for each sentence, you add it all up. Right? That is, in a sense, a measure of how surprised the model is by each sentence in the corpus. You add up all the log probabilities, and you divide it by the number of sentences. Right? That gives you the average probability per sentence. Right? So you always take this average, because if you don't take the average, then a big corpus is going to have a lower probability. Right? Because it's a product, so that doesn't really make sense. So you always take the average. You can do this per sentence, or you can do it per word. You can calculate the average information per word. Okay, this is called cross-entropy. Alright, so the idea is, you're given a set of events in a test corpus, which occurs with some frequency, right? So some events are more, if you think of them as words, some words are more common than other words. So each word occurs a certain number of times. And then we calculate this, basically this average, which gives you the average entropy per token. So essentially this comes out to approximating the entropy of the test corpus with respect to the model. So it's important to notice that it's a cross entropy, right? So because these probabilities are assigned by a model, right? But the frequencies are coming from the test corpus, right? So that's why it's called a cross entropy, right? So essentially you're measuring how much the model's expectations are like the corpus itself. If they really match up, then you get the lowest possible entropy. If they don't match up, then you get the poor entropy, right? So we'll see more examples of how that works out in a sense. So what is a language model? So what a language model does, there are different ways of doing this, but the simplest way to think about it is, it takes a test corpus, which is a bunch of words in English, and it assigns a probability to each word. Okay? The probability of the whole thing is the product of these probabilities. You consider them to be independent events. And if it's log scale, you can just add up the logs. Okay? And if it's a good model, then essentially it's going to say, this particular setting, if it's a well-designed model, which is aware of context, it's going to say that bank occurring in this particular setting is a high probability. All right, so how do you build language models? All right. So, it's like any other kind of model estimation process, right? So you have a large corpus and you have a model design, right? Then you have an estimation algorithm that produces the model, right? The easiest model that everybody's familiar with is regression models, right? You have, let's say, two variables, x and y. Y is dependent on x. You believe that the dependence is established by a straight line. Straight line has two parameters, right? It has an intercept and it has a slope, right? And then the estimation algorithm chooses the value of the intercept and the slope to maximize the fit and reduce the number of residuals, right? So if you have a least squares model, that basically assumes that the errors are distributed normally around the regression line, and the maximum likelihood estimate also gives you the least squares, same as the least squares error. So essentially the estimation algorithm finds the model parameters that maximize the fit of the model to the data. Okay. So it's the same thing here, right? We have similar types of things that happen here. And then what we can do is we can, given a test corpus, we can see how good this model fits it, and that measure essentially is cross entropy. Right. And so what this cross entropy is saying is, it's asking a model to assign a probability to each word or sentence or fragment in the test corpus. Right? If something happens a lot in the test corpus, right, then the model better give it a high probability. Okay? Because then the negative log of that probability is going to be close to 0, because the higher the probability, the closer it is to 0, so the information content is lower. Right? It's not surprised. Most often it's not surprised. Right? If something occurs very rarely in the test corpus, it's okay if it gives it a low probability. Because if you have a low probability, the negative log probability is high, which means there's more information. You're surprised to see it. Right? Now, if something is frequent in the test corpus, but the model gives it a low probability, that means the model is surprised a lot. It's like, oh, I didn't expect to see this word here. Why is this word appearing here so many times? It's surprised a lot. So that means the entropy will be higher, right? So a good model will give frequent events a low probability, and frequent events a high probability, right? It expects to see frequency but often. And rare events can be given a low probability, right? And of course, since it's a probability model and it's a discrete event space, the probabilities have to add up to 1, right? So it has to choose it properly so that the frequent events get high probability and the infrequent events get low probability. So if it is a good model and the test corpus is similar to the training corpus, you will get a good fit. In other words, the entropy will be lower. So this is really important. If you don't follow this, please ask. Yeah?
What about a word with different meanings? And what about the order of the words in this one?
Yes, okay. So the order of the words really matters. So in most cases, the models use context. So the models try to predict a word in context. So we're going to see how that happens in a minute. So that really matters. As far as the meaning is concerned, it's a great question. So the question is, in some sense you can say, should the model be aware only of the words themselves or the meanings of the words in context? Right? Would the model be better behaved and give you better results if it was actually aware of the meaning? Is that your question? Yeah. It turns out it doesn't matter. So it turns out Markov type models, which just consider the previous 2 words, are better than anything else. People have tried to build models based on parameters. People have tried to build phrase structure models and more complex models that are based on topics and so on. Nothing works better than linear models so far. It's very strange. And it probably goes back to some deep psychological property of humans, limited amount of memory we have, that makes us choose our words sort of with very local amount of information, sort of in the Markovian way. We don't remember a lot of previous data, we just choose based on our local remembrance. There's actually a very nice article in Savant magazine about why Chomsky was wrong, the deep structure models and grammar. There's a lot of new stuff in linguistics that Chomsky was wrong about all this. Somebody else has it. Okay. So this is kind of at the core of a lot of how statistical language processing works. All of it is about language models. So most of the work in statistical language models is different types of models and how the models are estimated and how they're evaluated. Okay. So what about language models? So they're really much more complex than your regression model, right? So a typical regression model that you do in empirical software engineering might have 10 variables. 10 variables is a really complex model, right? So some of the work that's coming out in GitHub, they model different things like, the number of committers, the number of bugs, the number of changes, all this kind of stuff. 10 variables is a complex model, right? Here you have literally trillions of variables that are being estimated, right? In most cases, the models are much more complex than the amount of data that's available. So what does that mean? If you have 10 samples and you fit a regression model with 10 variables, you're going to get a perfect fit, right? And it's going to be a wrong model because it's not going to be right for anything except your data, right? So I don't know what the rule of thumb is, but there's some kind of rule of thumb. You should have something like 20 times the number of samples as your variable, something like that. I don't remember the exact number. But you should have a lot of variables, a lot of data compared to the variables you have. In natural language processing, you never have enough data. You never have enough data, right? You always have a lot more variables than you have data. So what do? Well, you have to make do a lot of what's called regularization. That is, you make the models as small as possible, as simple as possible, so that you don't fool yourself by overfitting to the data. Right? So it's a big deal there. I think we'll get some time to talk about some of that. If not today, then maybe Dennis will get into it tomorrow. Different types of smoothing techniques.
I count on you because tomorrow I'll just...
Okay. Okay, I'll try to get into smoothing. But this is very important phenomenon. It's also a phenomenon in deep learning. If you've looked at deep learning, you've seen regularization. It's kind of because again, in deep learning, you have a lot of variables. And unless you fit properly, you're going to overfit. Okay, so you almost always face this issue of data sparsity, and there are particular kinds of estimation techniques in natural language processing that minimize the risk of overfitting. Right? because it's always a problem. All right, so how do we estimate a language model's quality? Is that the sentences or words or sentences or fragments of programs that the language model sees are not very surprising to it. So a good model, when it sees things more often, it will give it higher probability. Right? So if it sees something more often, it's not surprised. Yeah, I expect it to see the very often because I know the occurs very often. So after European and Central, I expect to see back. I'm not surprised. And of course, since it's a probability space, if you get high probability to something, you must give low probability to something else, right? Because it has to add up to 1. So infrequent language events can be assigned a low probability. It's something that's rare, you can say, okay, I'm not going to expect to see this, so I can give it a low probability. Okay, and this is measured using cross-entropy, as we saw before. So just a little bit kind of pictorial aspect of looking at cross-entropy. So you have a language model, and this is some program that is never seen before, it's a test program. And if you want to ask the question, what is a good description, we use cross-entropy. So if the model says, let's suppose there are only 6 different words, or 6 different events, right, in the language, very restricted language, there will be 6 different events. And let's say it picks a probability like this, the language model gives this kind of probability. Now, when you look at the test corpus, and you see the same distribution, then this is a good model, right? So the cross-entropy will be the same as self-entropy, because it's a good fit, right? And this case, the self-entropy you can see is a very low self-entropy, because it's heavily loaded. One event occurs most of the time, the other events never occur, so it's a very low entropy distribution, okay? So if the test corpus looks the same as the model, it's low cross-entropy. Is that clear? Yeah? So this is the ideal scenario, right? The low cross-entropy. Now, if the model thinks that this is what the world looks like, but the world actually looks like this, it is the worst case, right? So what does that mean? The model says event number 1 is rarely going to occur, right? I don't expect to see this very often, right? So the model says, I'm never going to see this word. It's a very rare word. But in the test corpus, it occurs the most often. So over and over again, the model sees this word in the test corpus, and it's really surprised. Right? So over and over again, it's getting very high negative log probability, because according to the model, this probability is low. So this negative log probability is occurring with high frequency. So it's getting high entropy scores on average. This is the worst case. Is that clear? Okay, so just to repeat, so this is essentially, there's a set of events in the test corpus, which occur with those frequency. And with the model, we basically calculate the, this sort of weighted average, according to the model, what the negative log probability is. So if a high negative log probability occurs repeatedly, that is, in other words, it's seeing something that is supposed to be rare and seeing it very often, then you're going to get a high score. Right? And so this approximates that. So everybody comfortable with the notion of entropy and cross-entropy, the difference between entropy and cross-entropy, and how a good model gives you low cross-entropy, a bad model gives you high cross-entropy. Okay. Right, so now we get into some experiments. Right, okay. So this is from an XC 2012 paper. We looked at a bunch of different Java programs and a couple of English corpuses. So those are the, something like 10 different Java projects. And this is 2 different English corpora. One is Brown, the other is Gutenberg. So in each corpus, you can see the number of lines, the total number of tokens, and the number of unique tokens. The unique tokens means a dictionary, how many different unique words are there in the corpus. Okay? So you can see for English, in Brown, you have about 56,000 unique tokens, about 1 million total tokens in the corpus. Okay? And so on average, you can see each token is repeated about 20 times. That's on average. Right? And then you have, for Gutenberg, you have 51,000 tokens, and you have 2.6 million total tokens, 51,000 unique, so each token is repeated on the average about 50 times. Okay. Now we get to code, and the one that is kind of the 2 extremes, you can see one extreme is Eclipse E4 here. Let's see if I can get this to work. I was afraid to do this because I'm afraid that accidentally shine this on somebody and blind them. Try not to do that. What did I do? Oh, Keynote quit. So I guess this is not going to work. Oh, it works. Okay. Right, so you can see Eclipse here, this one extreme. So there's 100,000 unique tokens, okay? Much more than English, right? So there's twice the vocabulary of English. And the smallest one is log4j, which has 8,000 tokens. And you can sort of divide out one by the other, and you can sort of get a sense of how terminologically rich different projects are. Some projects are very inventive, right? So they have, they have smaller size in proportion to the number of different tokens, and other projects are very prolific in terms of how they invent new vocabulary terms. Okay, so what we're going to do with this essentially is we're going to train a language model and we're going to test it to see how well it works. Right. Okay. All right. So how are we going to do this? Right. So the way we're going to do this is to do a plot like this, more plots, right? Exciting plots. Okay, and we have 1 gram, 2 gram, 3 gram, 4 gram, 5 gram. So what does this mean? So what we're going to do is, we're going to predict a word based on no context, not knowing anything about the previous word. Okay? With 2 grams, we're going to predict a word based on 1 previous token. 3 grams based on 2 previous tokens, and so on. Okay? So in this case, we know nothing except the frequency of the word. Right? So in English, we're going to predict the occurs most often. Okay. In Java, we're going to predict probably that open parentheses or close parentheses occurs very often. It's probably the most common thing, and so on. Right? And so, so 2 grams, in English it's probably off the, right? In Java, it might be close curly semicolon or something like that. So 2 grams, 3 grams, and so on. Right? Okay. So the y-axis is cross entropy. So what does it mean? Essentially, how much information is in that token? Okay. So in English, for example, we have roughly 50,000 words of vocabulary, right? 50,000 words of vocabulary. If every token occurred with equal frequency, we saw log to the base 50,000 is about 15 bits, right? So something like that for English would be 15. In Eclipse, it's a bit higher, right? So we have something like 100,000, which is maybe 17 bits, so we should see 17 bits, right? So now, what do you expect the shapes of these curves to look like? Should the entropy increase or decrease with increasing size? Sorry? It should decrease, right? Why should it decrease?
So now the previous word we can make an educated guess.
We can make a better guess. So if we know the previous word, we should be less surprised by the next word, right? So very often we should know what the next word is coming, right? And as we go along, we should see decreases. Do you think it will continuously decrease?
There will be a sharp decrease from 1 to 2 and then it will flat.
Why flat?
Because with the 1 gram you have no idea what to expect. And if you know the previous word, you have a good idea of what's to come.
Right. And then when you get to 3, you have more idea, no? Or 5?
I guess it won't be as significant as the jump between 1 and 2.
Yes, it'll be, you have some traditional information, but maybe you have less information. It depends on the nature of the language. In some languages, the 2 previous words might give you a lot of information. In some other languages, they may not. It depends on the structure of the language. The one thing that is interesting is, as you get to 4 and 5 grams, as you get to these things, how are we doing this, right? With a unigram model, that is each token, each word, we have a predicted frequency. How many parameters are there? You remember, go back to the regression model, right? With 10 predictors and 1 response, you have 10 parameters that you can estimate. With 10 parameters, Okay, so you need about 300 samples to estimate 10 parameters. So one parameter, 30 samples, it's just a correlation, right? With y dependence is just a correlation. You start 20 and 30 samples to get a good correlation. How many samples do you have for a unigram model in English? How many variables do you have, and how many samples do you have? How many variables in a unigram model for English? So you have to have a frequency for each word, right? How many words in English? 50,000, right? So how many parameters are we estimating for the unigram model? 50,000. How about for a bigram model? 2.5 million, 2.5 billion actually, 50,000 times 50,000? 2.5 billion. Okay, my head is starting to spin. Okay. Right. So how about for Eclipse? We have 100,000 unique tokens. So for a unigram model of Eclipse, 100,000 tokens, right? For a bigram model, 100,000 times 100,000, 10 billion. Okay, so it gets a lot worse, right? So you have a lot of parameters to estimate, right? So that means that once we get past 3, 4, 5 grams, we have huge amounts of parameters. And if you think about it, right, how much data do we actually have? Right, so, how much data do we have? We don't have that much data, right? We only have, in Eclipse, we have 6.8 million tokens. Even for a bigram model, we need billions of parameters to estimate. We just don't have that many bigrams. We just don't have bigrams. 50,000 times 50,000, 100,000 times 100,000 possible bigrams, which is 10 billion bigrams. And really, we only have something like 6.8 million bigrams. We have an order of magnitude less bigrams. When we get to trigrams, we basically have zero data. We have no data. You might as well ignore the data. We have so many parameters, you might as well ignore the data. That's how bad it is. Right? So going back and going forwards a bit. So when we get to these higher order n-grams, we have a big problem. There's not enough data. Okay. Now, what we have now is something called Google n-grams. How many of you know about Google n-grams? So Google has put up all the n-grams. There's a thing called all your n-grams now belong to you or something. All our n-grams now belong to you, something like that. So they've made all the n-grams on the web public. So in fact, we're getting to the point where we no longer suffer from data sparsity for trigrams and 4grams. There's so much data there, right? It's just massive over the data. So what happens is, in most cases, when you go along, yes, you can do better with more context, but you don't have data. Okay? So you will see some kind of saturation in this because there's just not enough data. Okay? All right, so let's look at the actual plots. Right? So, I'm sorry about that. Can everybody see that? Should have made this lens thicker. Okay, so that is Brown corpus for English. Okay, so let's examine it a bit closely. Now look at this, right? So at the unigram model, it's 10 bits. Is that higher or lower than you expected? So we thought it'd be 15, right? Because it's 50,000 words. Log to the base 2 of 50,000 is about 15. Why is it only 10?